Let's get it turned on. Okay. Switches. Hang on a second. It's very dark. It's quite romantic, isn't it? Is that wrong? Is that wrong with me? Try that. Oh, it's quite nice. I quite like this light level. You're not going to fall asleep on me, are you? Not because of the lighting anyway. So I can start the lights. I think we might have to do without the lights if that's all right. Can you see okay? I actually don't know where the light switches are on this one. Hopefully, when we've got the screens on, we'll have enough light in here. Visualizer, display. Okay. Main page. Can you see okay with that? Oh, here we go. Lights on. There we go. Yay, there we are. Great. Marvellous. I did not know they were operating from that panel. Okay. Hello. So, hopefully you had a lovely study week. Week off or whatever. So where were we? We were talking about conductors. And we had that important statement about, let's see where we were on the sheets. There we go. Right. Let's zoom that out a bit. Okay, where were we? Last time. Seems like an age ago, doesn't it? About that lateral do. Is that focused all right? Slightly off, isn't it? I'll try it auto. Okay. We made this statement last time about the difference between the electric and magnetic field which you got as an electromagnetic wave was incident upon a conducting material such as a metal. Okay? And we remarked about the difference between the situation of dielectric, and the important statement about the dielectric was that K is real. And if K is real, then we can say that the direction of the magnetic field is perpendicular to the direction of the electric field, and therefore also perpendicular mutually to the direction of propagation K. Right? But we saw that in a conductor, K is complex. So therefore it's not true that these things are necessarily perpendicular to each other, and we expect there to be a phase difference between E and B. Okay? So the next task is to work out what that phase difference is. So let's calculate that. Okay, so we said that in a dielectric, the phase difference in a dielectric, that phase is approximately equal to 0, okay, which means that the electric field and the magnetic field are going up and down together as a function of time. Now in a conductor, we no longer expect that simple relationship, which is that the magnetic field is C times less than the electric field. Let's calculate it explicitly. It's still about K over omega, and we can calculate that as root mu r mu naught. So this was using the expression we got for a conductor last time. Okay, there's an extra omega squared that appears inside from that omega outside, and then we have that 1 minus I again, don't we? Okay. So if we calculate that, we see that the omegas cancel out there, and we have mu r mu 0 sigma, can you see that right, over 2 omega. The omegas jump to the bottom, and we still have that 1 minus I on the outside. Remember, that was the situation because when I had a good conductor, that it was the imaginary term in the dispersion relation. When I took the square root of it, I had those two terms. Okay? So we see those two components. We see that B over E, if we extract out the mu naught and epsilon naught, I can write down a 1 over C, which I expect to see as a general scaling. So that's my free space situation. Right? But it's modified. It's modified by mu r, the relative permeability, sigma over 2 epsilon naught omega, right? So the mu 0 has jumped out and the epsilon 0 has jumped in, okay? Because I've extracted 1 over C out of that expression. And I still have that 1 minus I at the end there, okay? So you can see that the magnetic field, if the conductivity rises, the magnetic field is bigger, right? And we also remember that mu r is often 1, so when we see this formula, that often disappears. Okay? Now this term on the right-hand side, I can rewrite it. Okay? Remember that 1 minus I is somewhere on that complex diagram. I'm going to write it down as, this time, as 1 over root 2 e to the minus I pi by 4. Okay, so a brief look at that, you can convince yourself those two expressions are the same. Okay, so that's that bit there. What is that telling me? It's telling me that there is a 45-degree phase shift. Phase shift, okay, between the electric field and the magnetic field. So they're both falling rapidly as a function of distance into the material. But if I were to plot them out, okay, that is Z into the material, the conductor, and I were to draw the electric field. So in the dielectric, the two things are matched together, whereas in the conductor, okay, there's a 45-degree phase shift between this E and this B. But remember, this is just the phase part, or the oscillatory part, the skin depth, right, delta, is still much less than lambda, this wavelength. So as well as this phase shift, there's also a rapid decrease in the amplitude as a function of depth. Okay? So that's one statement I can make. So let's compare our two situations. Let's write them down one more time, right? So in my conductor, as a summary, in my conductor, I just calculated that B over E is equal to 1 over C. That's my free space situation. Okay, mu r sigma over 2 epsilon naught omega. Okay, so I've taken, yeah, that's right. Okay, times 1 minus I. That's my phase term. There's another root 2 hiding in there, isn't there? But we'll ignore that. And remember that very, very often mu r is basically equal to 1. And we said in a good conductor that sigma, the conductivity, is much bigger than epsilon naught omega. And that tells you something. It tells you this square root term is much bigger than 1. So therefore, the magnetic field is much bigger than E over C. Okay? So we compare that to our free space situation, which is that it's equal to E over C. So the magnetic field is vastly increased in a conductor compared to what it would be in free space. It must have something to do with those charges moving around in the conductor. And we compare that to the dielectric, where B over E is about N over C, isn't it? Right? Where N is the refractive index. So we have an enhancement of the magnetic field with respect to the electric field in any material, but it's vastly increased in the conductor. And remember that in a dielectric, N here is of the order of 1, right? You know, it might be something like 1.5 in glass or something like that, okay? But it's of the order of 1, it's not much, much bigger. Okay? Right. Now, you can see that those terms there, they do look a little bit like the skin depth. So let's calculate, let's try and relate the skin depth and the magnetic field sizes. So we'll recall the skin depth. So recall that the skin depth was equal to root of 2 over mu r mu naught sigma omega. Okay? And again, I'm going to keep reminding mu r is very often equal to 1. See that? Say that, keep repeating that. So roughly speaking, we can usually say that delta is 2 over mu naught sigma omega. Okay. So we're calculating an example. Let's have silver. A common or garden metal, costs about 30 pence a gram. Okay. So you can use that if you go shopping for jewellery. Right? So gold is about 100 times the price of silver or thereabouts, and silver is about 100 times the price of steel. Give you a rough idea. £30 a gram for gold, that's a lot of money for gold. Anyway, so silver. The conductivity for silver, well, this is for the kind of frequencies we care about, which is, we're going to say, radio optical frequencies, that sort of thing. Okay. We'll say it's about 6.3 times 10 to the 7 per ohm per meter, and we're just going to put the caveat if it is a pure metal, okay? Because most of the silver you buy isn't pure, it's about 95% pure, might have other stuff in it. So let's pick a frequency, let's pick a nice round number frequency of say 10 gigahertz. Okay. We'll see why later on when we look at RF signals. The skin depth there comes out to be about 0.6 microns. Okay? So electromagnetic radiation of 10 gigahertz basically doesn't travel very far into a piece of silver. But let's calculate what the wavelengths are. So remember, it's the frequency that remains constant. So the vacuum wavelength, so the in vacuo, say that time now, wavelength is C over F. This is what you would say would be the wavelength of 10 gigahertz radiation. We assume it's basically the vacuum wavelength. But in the metal itself, of course, it's not that, it's been modified. Okay? Remember we said that lambda, well, that's equal to 2 pi delta, isn't it? Right? In other words, it's about 4 microns, right? It's vastly, vastly, vastly different. So make sure that when you're calculating the wavelengths, that it's a frequency that remains constant, and the wavelength inside, in this case the metal object, can be 4 orders of magnitude different. In this case about 8,000 times or so. So we'll see later on that when we talk about waveguides we have a similar sort of behaviour going on. The free space wavelength is not the same as the wavelength inside the object, or in this case inside the metal. Okay, so let's do another example. We'll look at the conductivity value, sigma, okay? And just as for the sake of argument, we'll assume it's independent of F, the frequency, which is clearly not always true, but it's approximately true at lower frequencies, where low means still quite high here, right? But we're saying hertz to say gigahertz. So if that is true, we look back at our expression for the skin depth. Okay, you can see that here the relative permeability is 1, and the sigma is constant, then it's simply proportional to 1 over the square root of the frequency. Okay, so delta, if I know the skin depth at one frequency, I can convert it to the skin depth at another frequency by multiplying the root of the square root of the ratios of them. So let's look at another metal. Let's try copper. I can't remember how much copper costs. Okay. So we've got copper. Well, its conductivity is not far off. It's 5.96 times 10 to the 7 per ohms per meter. Okay, and then you're going to say if pure. Okay. So we can calculate a few skin depths. Let's calculate them for 3 interesting frequencies. The first one is mains frequency, 50 hertz. Okay, so that's the copper wires in the walls. Let you put your kettle on, and there the skin depth is about 9 millimeters. All right. 10 kilohertz, well, that's like your audio amplifier, or the wires that connect the amplifier to the speaker. In that case, delta is about 0.6 millimeters. So get your calculators out, just check I've got the right numbers there, which I think I have. And then finally, let's think of a really high frequency, f equals 1 gigahertz. That might be something like, like a radar signal. You might be hooking up your radar transmitter to some signal source, and in that case, the skin depth is something like about 2 microns. And if you lump those all together, a handy thing to think about, this is for copper, is something like 1 over square root of 235 times the frequency, right? Because that 235 there is like mu naught sigma pi. Okay? What does that mean? It means if I want to carry an AC signal at 50 hertz, if I have a wire which is significantly bigger than 9 millimeters, then the electric field from that oscillating current will not penetrate more than 9 millimeters from the surface. So if it's a 50 millimeter thick wire, there's nothing happening in the middle, it's all happening on the outside. Okay? So there is a maximum usable size of cable which is dependent upon the skin depth. And as you can see, as I increase the kind of frequencies that I wish to transmit along the wire, the skin depth gradually decreases. So if I want to carry a certain signal, and I want to carry a certain amount of power, and I might be limited by resistance or other things like that, what I need to do is subdivide that single conducting piece into several wires, okay? Where I have independent surfaces along which I can carry the signal. Okay? So for example, your speaker wires don't have to be big and thick to carry an audio signal. They only have to be about 1 millimeter in diameter or so. Okay? And again, if I have very high frequencies, eventually I start becoming sensitive to imperfections in the surface, right? Because the typical imperfections you might have in the surface of material start to be of the order of microns or a little bit bigger. So you imagine that as you get to very high frequencies, you have to start worrying about those imperfections in the surface. That's another feature of this behavior. Okay. So that was the general behavior in a conducting material. And remember, what we were talking about was the dispersion relation and its consequences. We should probably start looking a little bit more about the motion of the electrons in that conductor, because we're now going to move on to look at plasmas. So, shall we dive in? So we should look at the motion of electrons in a conductor, and this is what we're going to call the Drude Model, after its inventor. Okay. So remember that our basic idea of the dielectric, by comparison, so in a dielectric, remember our original postulate was that we had bound electrons, bound to atoms, and therefore under the action of an oscillating electric field at some frequency omega, those electrons would experience, if they were moved by the electric field, they would also experience a restoring force. Okay? And this is under the action of some form of external electric field on top. So remember, we wrote down an equation of this sort, right? We had an equation like this. We had the motion of the electron. Okay, it had mass m and acceleration x double dot. We had some kind of damping term, okay, gamma, and we had some natural frequency which comes about because of the restoring force, okay, and we were able to match that idea to the idea of there being some preferred frequencies in the atoms. Okay, restoring force. And of course on the right hand side of that equation we had the external electric field which varied as a function of time. Okay. Now, we didn't say before, that's called the Lorentz Model, this time with a T. Okay? So that we've done that already, right? Now, what's different about a conductor? Well, of course, our basic statement about the motion of electrons in a conductor is that there is no restoring force, which obviously is going to change the behavior of the motion. Yeah, the electrons, at least the ones we care about, are unbound. They're free to move. So you can see immediately this is going to be similar to in a conductor as it is in a plasma. The electrons in a plasma are also free to move. So we can write down exactly the same equation as we did before, so maybe slightly laboriously, write it all out. And I'm going to write in that term for the restoring force again, Q e to the t, and all we could do, we cross it out. Okay. Now this is called the Drude Model, obviously, because that's the name of the section. All right, after Signor Monsieur Drude or something. So this model will apply to any situation where the electrons experience no restoring force. So it applies to plasmas and conductors. They can be treated in the same way, where the same physical phenomena arise. So we just remind ourselves, in a plasma, we'll define explicitly what a plasma is here. So a plasma, there are different kinds of plasmas, but the ones we'll think of here is effectively a gas of positively charged ions and electrons. And to start with, we'll think of them as having the same number density, which presumably means the ions are singly charged. Okay? And so we have equal average density, but we'll see in a minute that the average density is not the same thing as the local density. And they are also, obviously, therefore, electrically neutral. There are non-neutral plasmas. We're not going to talk about those. These are neutral plasmas. And under the action of an external electric field, well, because the electrons in a plasma are lighter by about a factor of 2,000, at least, okay? Right? Say it was hydrogen plasma, the protons which would be left behind after the ionization, well, they're already about 2,000 times heavier. Okay? And any other plasma of any other gas is going to be even heavier than that. So under the action of electric field, okay, it moves only the electrons. So I think we mentioned that before, right? So the protons or the ions or whatever, they're more or less stationary. Okay? And it's that statement that the ions in a plasma remain stationary under the action of an oscillating electric field, which allows us to equate the concept of the plasma to the conductor. It's only the electrons that are moving. Okay. So if an oscillating electric field passes over a plasma and the electrons start to move, and then I remove that oscillating electric field, the electrons are seeing a background which is quasi-neutral apart from the position where they were displaced. So I expect them to oscillate backwards and forwards. I also expect there to be some form of damping, but let's first look at the motion itself. So this is one of those little tricky calculations to get the correct values from. Okay, so it's worth looking at closely. So we imagine that if we displace some electrons, well, let's draw that situation. So imagine I have some background plasma. So I'm going to draw the layer that I'm displacing electrons from. Okay. So if I displace the electrons by some electric field, I'm obviously going to leave behind positive charges. Remember, our plasma is overall neutral. So I'm drawing the bits that have moved first, right? So I imagine I've moved some electrons and I've moved them to some other position. Okay? And of course, they may not all move the same distance, but let's just say they've all moved together under the action of an electric field, and they've moved some distance, and I'm going to call delta x. Okay? And remember that this is with respect to my original situation before I applied the electric field, so that everywhere else I have a situation where the ions, the positive charges, and the electrons are intermixed. So I have a background of my neutral plasma. Okay? So the charge density everywhere else, the net charge density is 0. So there's no forces acting on these electrons from anywhere else. The only force they're experiencing is from the ions they've left behind. Okay? So I've moved a layer of electrons. So these are my moved electrons. And I'm going to say I've moved them by some scale amount delta x, and I've left behind a layer, okay, of stationary ions. So remember, I'm saying that the electric field is oscillating backwards and forwards at a rate where the electron motion is much greater than the positive ions. Okay. Left behind. And now what I do is I imagine, if I were to turn off that external electric field, what does the electric field between those positive and negative charges look like? Well, the electric field there, so I'm imagining a large area, thinnish layer, and if I have a number density of electrons per unit volume, then the total electric field is just that. Ne delta x divided by epsilon 0. Okay? So N is the number density per unit volume of those moved electrons. Okay, you may wonder how many are moved. Well, we won't worry about it. It'll cancel out in a second. Okay. So I can write down an equation of motion for the electrons. So under the action of the positive ions, which remain stationary, equation of motion for the electrons. Well, they're seeing a restoring force, aren't they, right? And we're assuming that they're not colliding with the positive ions as they go by, so they'll be accelerated back towards that layer. They will then pass through that layer, and they will just oscillate to the other side. And in the absence of any other forces, any damping forces, they'll just keep doing that indefinitely. Okay? So the whole layer, we imagine, is moving. So that layer delta x is moving. And it's moving under the action of whatever that electric field is. And hey presto, we see that it is simple harmonic motion. Okay? So all I've done here is I've just equated the electric field from the moved layer with how big that moved layer is. Okay? So remember, delta x is some layer of electrons being moved, and I'm calculating the motion of that layer. Well, obviously that's simple harmonic motion, and it has a frequency given by omega p, which is given by this formula: omega p squared is equal to Ne squared over epsilon naught m E. Okay? So that is the so-called plasma frequency. You can see it's a fairly universal idea. Right. So of course, the way we drew it, we imagined an electric field pointing one way, which is displacing a thin layer of electrons, but we can imagine a displaced electron with respect to some background ions being moved in any direction. It should oscillate with respect to an otherwise neutral plasma with this frequency. Okay? And the important thing here is this density of the electrons. Okay? So if they have a number density of electrons, n, we have a certain plasma frequency, omega p. Okay? Let's write that down in another form. So omega p is this angular frequency. If we write it down as its actual frequency, we can write it down as 8980 square root n hertz. Okay? And this is true if we write down the number density in per centimeter cubed. Okay? All right. So you can see that if you look in the notes, you'll see there's different ways to write this down. But imagine I had, for example, a number density of electrons in the plasma of 100 per centimeter cubed. That would be 10, and therefore the plasma frequency would be 89 kilohertz. Okay? So they would be shaking around at 89 kilohertz. And because they're shaking around, imagine they're accelerating backwards and forwards, they should also radiate, shouldn't they? So these oscillations that will occur in the plasma, they're called obviously plasma oscillations. That's the normal way we see them described. They're also sometimes called Landmure Waves. You may see that occasionally. Okay. Okay. So that's our basic concept. We imagine that an electric field has displaced a thin layer of electrons. They will start to oscillate. Now clearly they don't just oscillate. They will undergo collisions. Okay? What are they colliding with? Well, we already know, don't we, that in a conductor the resultant current depends upon the applied electric field and some conductivity. So as again, we just remark that an applied electric field in a conductor does not create an ever increasing velocity of electrons. This is not a relativistic effect, of course, because the electrons are slowed down by collisions. Collisions with what? Well, in the plasma, those are essentially ions, aren't they? We expect them to be ions. There's nothing else there. Okay? So the electron's coming along, it sees the Coulomb field of a positively charged ion, and it experiences a force which directs it transverse to its original direction of motion. Okay? So that's a scattering event. In a metal, it's a little bit different, but basically the collisions are with defects in the lattice of metal atoms. Okay? So let's try and work out some features of that. Let's assume to begin with that the material we're looking at, whether it's the plasma or the metal, okay, is uniform, same in every direction, same as a function, same depending on where we are in it, and we're going to consider here some steady state motion, okay, in a constant electric field. Our way of understanding that. So obviously what that is, that's a current, isn't it? Okay. So there must be a typical velocity for the electrons in that situation. Okay. So there'll be a typical velocity for the electrons. There will be a mean free path between collisions, mean free path. Okay. So there must be some typical time between collisions. So I'm going to calculate a collision frequency. See what that looks like. Collision frequency, gamma c, which is simply equal to 1 over some collision time. Okay. So just to picture that, my electrons, this is a cartoon, isn't it, right? Imagining that as the electrons are trying to move through the conductor under the action of some electric field, okay, they must be moving to the left, must they? Because if the current is that way, the electrons must be going the other way, mustn't they? Right? With some drift velocity that we're going to calculate. And obviously we know that these collisions, they have some collision time, tau c. Okay. And these collisions, they're the kind of things that are damping the plasma oscillations. So these two phenomena must be related. Collisions damp plasma oscillations. So the kind of phenomenon that we're seeking to explain now. Okay. Well, we can obviously write down for this situation that the current is equal to the DC conductivity, and we'll call that sigma 0 times the applied electric field, and you've seen before that it's equal to NE times the drift velocity. That's easy enough. Okay, remember to put in some vector quantities. Okay, so that's the DC conductivity. Okay. But obviously we can relate the drift velocity in our sort of microscopic picture. Each electron is accelerating under the action of the electric field, but it only accelerates for a collision time Tc before it gets stopped, let's say. So I can relate that to the electric field straightforwardly. Me 1 over gamma c, okay, because the collision time is 1 over the collision frequency. So therefore I can relate the conductivity to the collision frequency. You can see here that sigma 0 can now be related to gamma c from that very simple model. Sigma 0 equals NE squared over m gamma c. There you go. That was easy. But we already saw this NE squared, didn't we? We saw that the plasma frequency that we just calculated was NE squared over epsilon naught m. So I can rewrite the DC conductivity in terms of the plasma frequency. Okay. And in terms of the collision frequency. So if I know two of them, I can calculate the other one. Okay. So I can now calculate the same thing I did before in the Lorentz model, in my dielectric model. I can write out what the polarization is doing. You know, if I imagine my oscillating electric field. Okay. So I can do the same thing we did before. Write a similar equation for the polarization P that we did for the dielectric model. Okay. We also called it the Lorentz model, didn't we? Okay. So just write out one more time. Acceleration of the electron, got the damping term, and write as the collision frequency here. Okay. That's the rate at which the objects are stopped. I've got no restoring force because the electrons are free to move, and now I have the applied electric field just like I did before. Okay. So I can write that solution down, and again I'm writing it down and I'm leaving in, to show the comparison, I'm leaving in the restoring force term, but I'm then crossing it out immediately. Okay, so you can see where it's appearing. Okay, so previously in the dielectric we had a restoring force and a characteristic frequency, but in this case we don't have that, so that term disappears in the expression for the motion of the electrons. Okay. So I look at this and I think, okay, well that's my solution for what the motion of the electron, that's its position x due to the action of an oscillating electric field. Well, I can just differentiate that, can't I? I can say that x dot is equal to I e omega over m. These should be me, shouldn't they? Okay. E0. If I missed any off, obviously it's the motion of the electron, so it's the electron mass. And I get rid of that. I'll ignore that omega naught squared. So I just have minus omega squared plus I omega gamma c. Okay. Now, if you look in textbooks, you'll see other ways of getting this result, right? I think it's Lorraine, Course and Lorraine should look in for this. But you already see that. See, when we differentiated the position as a function of time to get the velocity, well, of course, that's the velocity of the electron, isn't it? So we can relate that straight away to the current. We can say that the current J, which is equal to sigma E, is equal to NEV. Well, V is just x dot, isn't it? Okay. So again, we can relate conductivity, sigma. Okay, and this is now the conductivity for which is not DC. We can calculate the conductivity at different frequencies as so. Okay. So this is the conductivity as a function of frequency, and you can see straight away therefore that the conductivity at some frequency omega can be related to the DC frequency with an additional term to do with the collision frequency of the electrons with the atoms that they're passing by. Okay? So that's conductivity as a function of frequency. Okay. So far so good. So that's our Drude model. Now that was our term for that was our expression for the polarization. So remember we wrote down the polarization P. So it's just the same as the Lorentz model for the dielectric. The polarization at any instant can be written down as being due to the electric field of that instant. Okay, this is for some frequency and some with some value called the electric susceptibility. Okay. So our task now is to try to relate that electric susceptibility to the properties of the conductor or the plasma in this case. Okay. So we'll write that down. So P is a function of time equal to epsilon 0 times the susceptibility. Okay, so we're writing explicitly the electric field has some peak value and it's oscillating at some frequency omega. Okay. So this is just the same as we had for the dielectric. Okay. But now we have Ne squared over M. Okay, that was the model we got above us, up here. Okay. And again, just to show the comparison, I'm going to write in a term and then immediately delete it so you can see how it relates to the dielectric model. Okay. And the difference here, of course, there are no restoring forces, there are no atoms of different kinds. So therefore there's no sum here either. All it depends upon is the number of conductors per unit volume and upon the rate at which the electric field is varying. Okay? So you can see I'll put the omega in there to compare it with the dielectric model that we had previously. So just like before, we can write down an expression for the permittivity. Remember, it's simply that's another way of writing down the susceptibility. So again here, it's 1 plus E squared over M epsilon 0, the density of the electrons in that conducting material or in the plasma, and it depends upon the applied frequency and the collision frequency. Okay. So this is the permittivity of a conductor. And if we look again at this electron density here, we can replace that with the plasma frequency. So we can relate the permittivity of a conductor to the plasma frequency in that conductor. Or again, similarly for a plasma. Okay. So this is the permittivity in a conductor or plasma. So that's my basic expression. Okay.
Should there be an equal sign instead of a plus on the line above?
Yes, there should be. Sorry, yes, that should be an equal sign. Yeah. Thank you. Okay. So we've got two parallel derivations. We have a density of objects, n, and we have two expressions for permittivity. So it's similar to what we did for the dielectrics. We should look at interesting situations, shouldn't we? Probably not going to get to look at both of them today, but this week we certainly will. So what interesting situations are there? Well, obviously it all depends on the frequency. So what are the interesting regimes? Well, you just by observation of this expression, first situation we're looking at is when the frequency of the radiation passing over the conductor is much less than the collision frequency. Okay? So let's write down what that looks like. We can say here, just by inspection, that the permittivity at low frequencies looks like the following. So let's write it down in terms of the electron density. Okay, 1 over I omega gamma C. Okay. And if we look carefully, we can recognize that that is equal to 1 plus sigma 0 over I omega epsilon 0. Right. So at low frequencies, which means low compared to the collision frequency, we also now need to look at the relationship between the conductivity and the frequency again. So it depends what kind of conductor. So at low frequencies and in a good conductor, okay, where sigma is much bigger than epsilon naught W. Okay, that's similar to what we saw before, wasn't it? We can write down that epsilon r, the permittivity, is basically complex valued. It's I sigma over omega epsilon 0. Okay, what does that mean? Well, we write down that the refractive index n can be related to the relative permittivity. Okay, just note down this is the refractive index and not some other density of something. Okay. And we do our normal trick that we did before. We're going to write n as being equal to a real part and an imaginary part. Remarking again, we need to be careful of the minus sign and the I in how we describe the attenuation. So there's obviously going to be an absorptive part. Okay. We can rewrite that in terms of the real part and the imaginary part of the wave number. Okay, so the real part's obviously the oscillatory motion, and the imaginary part is the attenuation. And we see straight away that the real part and the imaginary part of the refractive index, their magnitudes are equal, and they're equal to the conductivity scaled by the frequency. And again, you see that 1 over root frequency appearing again. Okay. And we've done the same trick as we did before, where we said minus I to the half. Okay, so I'm not going to do the full derivation here. It's equal to 1 minus I over root 2. That's where that factor 2's come from. Okay. So we can write down what the electric field in the conductor looks like. Okay, the propagation in the conductor. And you're going to start to see that, you're going to start to recognize this term now. So the electric field in the conductor, it varies. It's got obviously e to the I omega t. It's got a time variation, of course, right? And it's got a spatial variation. It's got an attenuation, which goes as 2 parts. We've got I omega over c nrz. Okay, that's just another way of writing how the phase changes as a function of distance through the material. And then you've got this e to the minus omega over c niz. So if we've got the i's and the minus signs right, then this should go down as we go into the material. And that's obviously like another skin depth term again, isn't it? So this is our conductor. So let's write that down. So the skin depth here, delta, if we look at that term in the exponential there, c over omega, 1 over the magnitude of ni, hey presto, c over omega. And we've seen this before, haven't we? 2 epsilon naught omega over sigma naught. Okay, and we can write that as root 2 over mu naught sigma naught omega. Okay, well that's the same expression we saw before. So this is the same expression as we had before. The difference is, this time, we've used an atomic model. This time, use our Druid model to obtain the actual conductivity, sigma 0. Okay? Which is kind of neat. I like that. Okay. So I think I'll leave that for today. So what we'll do is on Friday we'll go through the plasma we'll go through propagation at high frequencies through plasmas, and that will finish off this section. And then we'll move on to reflection, refraction, and scattering, I think. That's about right.
Fine.